Thanks everyone for coming today. We'll be presenting on our project, which is learning and auditing for subgroup fairness. Oh, clicker is not working. So my name is Adele.
I'm Will.
I'm Arnab.
And I'm AJ.
And we were advised by Professor Michael Kearns, and we also worked closely with Professor Aaron Roth and Seth Neal, who is their PhD student. So why do we need to audit machine learning algorithms? The news has been talking a lot about lately algorithms, bias, and how using machine learning algorithms could actually result in discriminatory results for people.
Yeah, and so how exactly is this discrimination happening from a machine learning algorithm? Well, in your typical machine learning pipeline, what you have is data that goes into a learning algorithm, and this learning algorithm is going to create a model that's going to be used for prediction. And an issue here is that, well, this learning algorithm, it's going to minimize some function of error over the entire data set. And so as a result, it may ignore some certain correlations in, say, minority populations. And a good example here is in recidivism prediction. And so recidivism is predicting the likelihood that someone that's leaving prison is going to commit a crime again. And keep in mind, judges are actually using machine learning software to inform their decisions about whether they're going to give people parole. And what they found here empirically is that some of these models, they're discriminating against people of color because people of color are twice as likely to be falsely labeled as a danger to society when they're actually not compared to the rest of the population.
So what can we do about it? There's been a lot of research over the past couple of years into building what they're calling fair algorithms. And so what this usually means is that we want a machine learning algorithm to satisfy some notion of fairness for a population. Oftentimes this looks like saying that the error rates or false positive rates should be equalized across groups, as otherwise would count as some kinds of bias. And there's a few different ways people have gone about achieving them, but typically all the existing approaches generally only allow you to look at one kind of group distribution. So maybe this is fairness with respect to race, or fairness with respect to religion or gender or age, only doing one of those in isolation. And we think that that's a problem. And that's part of what our project is aiming to address.
Okay, so we'll just use a lot of terminology, but let's try to break this down into a simple example. Imagine that all those dots we have up there are eligible students for our school. But we only have so many spots, we need to pick. Right now, all of the students, they are either male or female, and either blue or green. And if we took only the red circled individuals, and we're only looking at marginal fairness, so just the rate of males versus females and blue versus green, well, this actually satisfies marginal fairness. But inherently, there's something wrong with this picture. And that's subgroup fairness, and that is what we are trying to address with our solution.
Yeah. And so when you're looking at the field of fairness in machine learning, there are some inherent challenges that have been witnessed in the literature that we kind of have to work through with our project. So one of these is that, as Will mentioned, there are different metrics for fairness. There's false positives and false negatives. And what you find mathematically is that sometimes it's impossible to have more than two of these at a time. Another problem they have to deal with is that fairness isn't free. So when we're adding a fairness constraint to a machine learning model, where we're effectively saying that there are certain models that we can't use, and it's very possible that the model with the best error overall is something that's going to be unfair. And so what you get is that as you kind of change the parameter of fairness that you're looking at, well, it's possible that there's going to be a trade-off between fairness and accuracy here. And finally, you might just be asking, well, why don't we just remove the protected attributes like race and gender and age from our data set and then train a model off of that? Well, machine learning is a lot about correlations, and if you have correlated data, well, they found empirically that just removing these protected attributes will still result in bias in many situations.
So what can we do about it? Our project and our solution is an open source software package for fair machine learning, specifically with a focus on subgroup fairness. It's available now on GitHub, and anyone can download it and train and audit a fair classifier with just a few lines of code. This is designed to be something accessible to individuals without much background in machine learning, and we provide tools both for creating the algorithm itself and for taking an existing model that you already have and understanding how biased it is and for what parts of the population. How does this actually work? So this algorithm, first we take in data and make sure that the data is appropriately formatted, but the real key here is this inner loop between a learning system and an auditing system. So what's really happening here? The learning system is like what Arnab talked about before, where we simply are trying to find a good, predictive, accurate classifier that makes as little error as possible. Then our auditing stage finds parts of the population where this classifier is violating the fairness constraint for subgroup fairness. And so by identifying these groups, it then feeds back that information into the learning process, which then corrects its decision-making to alleviate that bias. And eventually, as our algorithm runs, it converges to a classifier which satisfies fairness across all subgroups. And these are some visualizations of what's going on here. So on the left, this is what we call a Pareto curve. And so what this means is that there is an inherent trade-off between fairness and accuracy, as Arnav mentioned. As you vary a parameter specifying how much unfairness you're willing to tolerate, you end up getting a higher error as a result because you're further constraining what your model is able to do. But we think that there's not necessarily one correct use case for many scenarios. And our goal with this project is not to tell people this is the right fair classifier to use, but rather here are your options, here are the trade-offs that are available to you, and we want you to understand what these trade-offs mean for any one use case, whether this be loans, admissions, or other applications where we care about fairness. On the right, this is a visualization of our algorithm actually running in practice. You can think of each of these little squares on this rotating plane as a group of the population identified by one of these two variables. And so what you can see is that as the algorithm runs, the error rates for false positives are quite different at the start. And then eventually the algorithm identifies these issues and kind of patches itself up, eventually smoothing out this surface, identifying that we have solved the issue of subgroup fairness for this data set.
Yeah. And we've packaged this all into a really nice UI that we hope is intuitive for users. We've modeled it after scikit-learn, which is sort of the standard machine learning in Python. And you can create a model, you can train it, you can use it to predict new data, all within 3 lines of code. We also provide our sort of tools as one-off tools like an auditor. So this means you can audit other predictions from other machine learning models, as Will said you might want to, and you can identify subgroups that are unfair. And we also provide the code sort of like this for creating the Pareto curves, for creating the heat map, so that we let users decide what final model they want and what is the trade-off.
How did we go about evaluating our system? So we thought it was important to see, like, okay, once we have the code, once we have the algorithm, can people actually use this? Is this intuitive? Is it user-friendly? And so we set off on a multi-pronged approach. For one, we had the opportunity to have our code presented at the Fairness, Accountability, and Transparency Conference in Atlanta this year. And so this is a conference of researchers across academia, a lot of them in computer science, some in fields like sociology, looking at issues of bias and unfairness in AI and algorithms. And so we were able to get a lot of good feedback from practitioners in academia and industry saying what they liked about our project, features that they suggested we add, and generally people seem to be very excited that there's a growing effort to make tools like this accessible to data scientists.
Yeah. We've also been able to sort of see this in a classroom setting. We partnered with a computer science class here at Penn, SIS 399, the Science of Data Ethics, which used our software in one of their homeworks. And from this, we got 40 students who were able to use our code, and we got feedback from them. We had them fill out a form. Here are some quotes, and we got some more empirical data from them too. So I said 40 people, 75% of which had little or no machine learning experience coming into this class, which means you really got to see, in the previous example, we got people who research machine learning and know the literature, know scikit-learn. And here we got to see, okay, what about people that don't really know it? How intuitive is it? And we asked them on a scale from 1 to 5, how helpful were our visualizations? How easy was our code base to use? And we got great results. We got 75% gave us positive feedback on the visualizations, and 50% rated us 4 or 5 on how easy our code was to use.
And kind of the final prong of our evaluation is from industry, and this is something we're pretty excited about. IBM, they're always trying to be on the edge of innovation, and so they are actually trying to become a hub for fairness and machine learning, and open source packages for that. And this is called AI Fairness 360. They noticed that they had a gap in the packages that they had acquired so far, and they were not taking into account subgroup fairness. They saw our code at the Fairness, Accountability, and Transparency Conference, and they reached out, and we were actually working to integrate with them, and that will be soon live as well. So what's the story here? Machine learning is everywhere. It's affecting decisions that we are a part of every single day. And we want accountability. And auditing is one way to help us get that. We think subgroup fairness is just one definition of many that will help make machine learning algorithms fair. And by making this open source, we are increasing the accessibility to data scientists everywhere to create fairer machine learning that we have to use and interact with on a daily basis. Thank you.
Any questions?
Yeah, very interesting. And my question is more philosophical. Who decides what's fair? You use the word fair over and over
Yeah.
and over.
That's a great question.
It's not objective.
Right. So yeah, this is a very important thing to point out. And so there are a lot of different definitions of fairness that people toss around, and not any one of them is necessarily right. There could be no right definition, but one thing that we do is we allow people to have a couple different options. So some common ones people look at are equality of like false positives or false negatives across different groups. You could also ask for equality of error overall or other metrics that you want. But the idea is that if you know what metric you use, you want to be able to satisfy that with an algorithm. So we're not necessarily saying that we're telling people this is the right metric, but if you know what metric you want, you can use our algorithm to get there. Any other questions? Yeah.
You applied as a gender, there was something we were going to you look later algorithm to get there?
Sorry, can you repeat that?
Two clients as a gender. They use our algorithm to manipulate something.
So our algorithm has a pretty strong theoretical guarantee behind it, which says that like if you use this approach to train your model, it's going to satisfy this set of constraints. And so our goal is not for people to use this to manipulate their marketing. Our goal is that we think that there's a lot of scenarios where you actually want some kind of fairness. Let's say you're doing allocation of loans to people. You're using some algorithm to predict whether someone's creditworthy. We think that it's important for these systems to not be biased against certain populations. And we think that we would hope that companies take this seriously, that it becomes a goal of many tech companies, and we think that there's a growing concern that this is a real issue. So we hope that it can be a positive set of tools for people to use.
Just as you said it now, you've actually opened up the market for the product, that you use it as an auditing tool.
Right. Mm-hmm. Yep. So
Yes.
we think
Instead
that.
of it being like a company using it, now you bring it in and say, so you're supposed to be fair. Let me show you how fair you're not.
Right.
Yeah, that's
Yep.
actually a really good point. There's another thing at Penn called the AlgoWatch Initiative. It's a website that's actually going to use our auditor on different algorithms that are like being used by companies today.
Right. And so we think like, at least for now, we think that the actual algorithm itself is something that maybe a giant company is not going to be willing to trust to put into production. It's open source code, but we think that the auditing system that we built is going to be very useful for researchers who maybe have other approaches that they want to use, but they still want to make sure that their approaches are satisfying fairness.
Does this apply to databases too?
So all of this is kind of built on top of pandas. So if you have something that you can convert into a pandas data frame, that works. It's you could so if you have like a SQL database, you can run pandas queries against those. Yeah.
Have you guys looked at this in particular with reference to the compliance requirements around the Fair Housing Act advertising?
Not specific.
So from what I understand, the Fair Housing Act is the way that, are you referring to Facebook's violation of that? Okay, so just to like give some background, I guess, Facebook is being accused of violating the Fair Housing Act because they were allowing advertisers to show ads on housing based off of like protected traits such as race or gender. This could be used in that sense for sure, but we don't have like a database or anything like that that we've like tested it on there.
Maybe I don't know enough about the sort of machine learning background, but data that you use to determine, like to train your model, does this address the fact that maybe some of those data have biases in them based on like what human labeling like went into that?
That's a great point. And so this is really addressing just this one stage of the pipeline. So this says that the algorithm, once you train it, if you assume that the data you have in your training sample is the same distribution as the data in the wild, then the guarantees will hold. If the data that you have is like completely obscured, there's really no way that you could hope to promise anything about what your algorithm will do on data from a different distribution. But we also think that that's an important process. And so we think that the auditing systems can be useful for checking whether there is bias in what you have already to start.
Thank you very much.
Thanks.
Thank you.